Hi guys, in this video we'll take a look at the rules of differentiation, rules in differentiating polynomials, examples, and then we'll finish with a summary.
So what are some of the rules that we use when performing differentiation? Recall that the method of differentiation from first principles can be used to find the derivative of a function. We now have a direct formula for the derivative or gradient function of a function. Suppose we're looking at the function f of x. Then the derivative f prime of x is equal to the limit as h tends to 0 of f of x plus h minus f of x divided by h. We can investigate how the initial function has changed after applying the method of differentiation. For example, if we start with f of x is equal to x squared, then it turns out that f prime of x is equal to 2x. Or if we start with g of x is equal to 3x, then g prime of x, its derivative, will be equal to 3. And if we start with h of x equals 4, then h prime of x is equal to 0. We'd like to be able to relate f to f prime, g to g prime, and h to h prime in order to determine a general rule for differentiating these kinds of functions. And as such, we can come up with some general rules for differentiating polynomials. So what are the rules for differentiating polynomials? Consider finding the derivative of the function y equals x squared using differentiation from first principles. So we have that our y is equal to, in general, f of x, and in particular f of x we're considering is x squared. So if you wanted to look at f of x plus h, which would be necessary for computing the derivative, then we can just substitute in x plus h, and we get x plus h all squared. This is equal to x squared plus 2xh plus h squared. And so now if we want to find our derivative f prime of x, then of course we look at the limit as h tends to 0 of f of x plus h minus f of x divided by h. Then by substituting in, we get the limit as h tends to 0 of, well, f of x plus h is x squared plus 2xh plus h squared. And then we minus our f of x, so we minus our x squared. And then we divide by h. If we then subtract and divide, we get that this is equal to the limit as h tends to 0. Well, x squared and x squared cancel out. And then by dividing, we only have these two middle terms to divide. And we get a 2x and a plus h. Of course, as h tends to 0, h tends to 0, and so this is only going to be 2x. If we were to repeat this process to find the derivatives of the functions y equals x to the power of n, where n is a real number, we should notice a. So if we were to apply our process to find dy by dx, and of course, since this is equal to f prime of x, this is going to be equal to the limit as h tends to 0 of f of x plus h minus f of x divided by h. And we can do this process on a few different functions of x, namely y equals x to the power of 1, as well as y equals x to the power of 3, and then perhaps we could measure y equals x to the power of 1/2. Doing differentiation on these three different polynomials yields the following. Firstly, we have dy by dx is equal to 1, and then for the second one we have dy by dx is equal to 3x squared, and then for the third one we have that dy by dx is equal to 1/2 x to the power of minus 1/2. And so the first thing to note is that between y and dy by dx, the power from before in the y comes down to the front in the form of a constant in the dy by dx. So in the first case we have this 1, which becomes a 1 outside, and we have this 3, which becomes a 3 outside here, and we have this 1/2, which becomes a 1/2 outside here. So the power comes down in front. And similarly, looking at how the power itself develops from y to dy by dx, at first we have an x to the power of 1, and then we have a constant term, and so the power has reduced by 1. Similarly, from x cubed to 3x squared, the power of x has reduced by 1. And finally, from x to the power of 1/2 to 1/2 x to the power of minus a half, again, the power has reduced by 1. This allows us to generalize a rule for differentiating f of x equals x to the power of n for all real values of n. So if we have that f of x is of the form x to the power of n, then this gives us that f prime of x is equal to, first, bringing down the power to the front and giving a constant outside, so our n goes there, and then we reduce the power by 1. So we have an x to the power of n minus 1. Recall that differentiating a constant from first principles gave 0 as the derivative. Let's say we have our function of x, f of x is equal to 4, as an example of a constant. Then, similarly, if we consider f of x plus h, by substituting in x plus h everywhere that you see x, you're also going to get 4 again for f of x plus h. And therefore, if we consider our derivative f prime of x, using our formula, we're going to get the limit as h tends to 0 of f of x plus h, which is 4, minus f of x, which is also 4, divided by h, and this limit is 0. We can include this in the general rules for differentiating. If we have that f of x is a constant a, then f prime of x is equal to 0. But again, it's important to note that a is a constant. Notice that multiplying the function f of x by a constant a also results in the derivative f prime of x being multiplied by a. So if we consider our first few examples we had before, but each one multiplied by a, so for our first one we have y is equal to a multiplied by x to the power of 1 this time, and our second example was y is equal to, this time, a multiplied by x cubed, and then for our last example, y is equal to a multiplied by x to the power of 1/2. Then if we go through the same process of differentiating, we find that dy by dx is equal to just a rather than 1. For the second example, dy by dx is equal to 3a multiplied by x squared. And then for our final example, dy by dx is just going to be equal to 1/2 multiplied by the a multiplied by the x to the power of minus a half. And so in all three examples, all that's happened is we've taken our earlier derivative and multiplied it by a everywhere. And this allows us to generalize a rule for differentiating f of x equals ax to the power of n for all real values of n, and a constant a. In general, suppose that f of x is of the form a constant multiple a, lots of x to the power of n. Then our derivative f prime of x is going to be equal to the constant a multiplied by n x to the power of n minus 1. So again, all that's happened is we've taken our earlier derivative of x to the power of n, which is nx to the power of n minus 1, and by multiplying an a to the function, multiplies an a to the derivative. Consider differentiating the following function. Let's say we have the function f of x is equal to x plus 1 all squared, and we'd like to find this function's derivative. We should first expand the brackets to write each term in the form ax to the power of n, where a is a constant and n is real. If we consider our x plus 1 all squared and expand it out, then we end up with x squared plus 2x plus 1. And so our function f of x is actually equal to x squared plus 2x plus 1 by the expansion. And then in order to differentiate this function, we can differentiate each term separately in order to find the derivative. We have seen that in general, if we have a function f of x is of the form ax to the power of n, then in order to differentiate it, we get our f prime of x is equal to an multiplied by x to the power of n minus 1. And therefore, if we look at our function, f of x is equal to x squared plus 2x plus 1. And so to differentiate this function of x, all we need to do is to differentiate each term completely separately and add up the results of each derivative. And so starting with x squared, we have our a is 1, our constant out the front, and we have our x to the power of 2, so n is 2. And so our derivative is an, which is 1 times 2, which is 2 for our constant. And then we have x to the power of n minus 1, which is x to the power of 2 minus 1, which is x to the power of 1. And then we have our 2x term. This corresponds to a equals 2 and n equals 1. And so an is also 2 for this term. And we have our x to the power of n minus 1, which is x to the power of 1 minus 1, which gives us x to the power of 0. And as we've seen, differentiating 1 just gives us 0 because 1 is a constant. And therefore, the result for f prime of x is 2x plus 2. But again, the key thing is that we can just add up the derivative of each term in order to find the derivative of the whole expression. We can use the rule for differentiating ax to the power of n to differentiate functions with more than one term by differentiating each term separately. In general, if y is equal to f of x plus g of x plus h of x and so on, then to differentiate this, all we need to do is our dy by dx is formed by differentiating each term separately and adding up the results. And so we have our f prime of x plus our g prime of x plus our h prime of x and so on. Let's take a look at some examples. Our first example asks us to find the derivative of the function f of x equals 4x cubed plus 12x squared plus 15. Our first step is to recall the rules for differentiation, including the fact that differentiating a constant gives 0. If we have our function of x, which is equal to ax to the power of n for a constant a and real value n, then the derivative f prime of x is equal to an multiplied by x to the power of n minus 1. Similarly, if we have our f of x is just a constant a, then when we differentiate it, we get our f prime of x, and this is just going to be 0. This is a rule worth remembering for speed, but it does just come from the first rule. It's the case that n is equal to 0. And because you have n is equal to 0, i.e. ax to the power of 0, which is just a because x to the power of 0 is 1, then the derivative is an multiplied by x to the power of n minus 1. Well, that is an n outside, and n is 0, and so you get the derivative as 0. But as we say, it's worth remembering for speed that differentiating a constant gives 0. Our second step is to recall the rule for differentiating functions that are the sum of functions that we know how to differentiate. In general, if y is equal to the sum of functions f of x plus g of x plus h of x and so on, then in order to differentiate this function, i.e. we get dy by dx, all we have to do is to differentiate each function in turn. And so we have f prime of x plus g prime of x plus h prime of x and so on. Our third step is to differentiate each term separately to find the derivative f prime of x. So we have that our f of x is given to us as 4x cubed plus 12x squared plus 15. And so our derivative f prime of x is going to be equal to, by using our differentiation rules, 4 multiplied by the value of n, which is 3, multiplied by x to the power of 3 minus 1, i.e. we bring the power down by 1, and we have plus 12, the constant outside, multiplied by the power, which is 2, multiplied by x to the power of 2 minus 1, and then the 15 just goes away. So we get a plus 0, because 15 is a constant. All this is going to be is 12x squared, and then we have a plus 24x. And this is our derivative. Our second example asks us to find dy by dx for y is equal to x minus 2 multiplied by 3x plus 4. Our first step is to expand the brackets to write each term in the form ax to the power of n. We have that y is equal to the two brackets multiplied together, x minus 2 multiplied by 3x plus 4. And so by expanding this out, we get the following. We have 3x squared, and then we have a minus 2x from the minus 6x plus 4x, and then we have a minus 8. Our second step is to recall the rules for differentiation. If we have that f of x is in the form ax to the power of n, then when we differentiate and we get f prime of x, then we'll get a multiplied by n multiplied by x to the power of n minus 1. Similarly, if we have that f of x is just a constant, i.e. f of x is equal to some number a, then when we differentiate we just get 0. So f prime of x is equal to 0. Our third step is to differentiate each term separately to find dy by dx. So all we're going to do is take our y, which is 3x squared minus 2x minus 8, and differentiate each term and add up the results. And so we get that dy by dx is going to be equal to, for the first term, our a, which is 3, multiplied by a value of n, which is 2, multiplied by x to the power of 2 minus 1. And then for our next term we have a minus 2x, which is a minus 2 multiplied by the power, which is just 1, because we have an x. And then we have an x to the power of 1 minus 1. And then for our constant term, which is a minus 8, we just end up with plus 0. And therefore all we get is a 6x for our first term, and then we have a minus 2. And this is our derivative. Our last example asks us to differentiate the equation y equals 2x squared minus x plus 3 divided by x to the power of 1/2. Our first step is to write each term of the equation in the form ax to the power of n. So our first step, sensibly, is to split up the fraction into 3 separate components. Our first component is our 2x squared divided by x to the power of 1/2. Our second component is minus x divided by x to the power of 1/2. And then our last component is plus 3 divided by x to the power of 1/2. And then by applying our index rules, we just get 2 multiplied by x to the power of 3 over 2. And then we have a minus x to the power of 1 over 2. And then we have a plus 3 multiplied by x to the power of minus 1/2. Our second step is to recall the rules for differentiation. We have that if we have a function f of x of the form ax to the power of n, then when we differentiate and get f prime of x, we just get a multiplied by n multiplied by x to the power of n minus 1. Similarly, if we have f of x is just a constant a, then if we end up differentiating it, we just get 0. So f prime of x is equal to 0. Our third step is to differentiate each term separately. All we need to do is to take our equation for y, which is 2x to the power of 3 over 2 minus x to the power of 1/2 plus 3x to the power of minus 1/2, and differentiate each term separately and add up the results to give our derivative dy by dx. And therefore we get that dy by dx is equal to the following. For our first term, we take our constant 2, and then we multiply by the power, which is 3 over 2, and then we have our x to the power of 3 over 2 minus 1. And then our second term is minus x to the power of 1/2, and so we have minus 1/2 from the power, and x to the power of 1/2 minus 1. And then for our last term, we have a plus 3 multiplied by the power, which is minus 1/2. And then we have our x to the power of minus 1/2 minus 1. And so therefore, our expression for dy by dx is going to be 3 as the constant for our first term, and then we have an x to the power of 1/2, and then we have a minus 1/2, x to the power of minus 1/2, and then we have a minus 3 over 2 multiplied by x to the power of minus 3 over 2. This is our expression for dy by dx.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level maths a walk in the park.